Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
So let's get started. So it's my pleasure to introduce David Mcallister, who is a professor and Chief Academic Officer at the Toyota Technological Institute of Chicago. Prior to that, he was faculty member successively at Cornell and MIT. And then he was at AT&T, a researcher at Bell Labs, then AT&T Labs. And he's a IIII fellow and has published in a lot of different areas, machine learning, of course, but also natural language processing, vision, AI planning, and automated reasoning, and I think a few others that I have missed. And so I just want to mention also that there are also options to meet with David. So Danny send a sign-up sheet around, and so either fill up the sheet or talk to me, send me an email, and we can certainly arrange something. So now I'll let David speak.
Okay. It occurs to me that we may have a problem with this talk in that there may be people in the audience who have seen it before. So there was a workshop on speech and language a year ago in Bellevue, and I gave this talk there. How many people have seen this talk before? Has anybody seen this talk before? Okay. At least the people who've seen it before didn't come. Okay, so we'll go ahead with this. This is joint work with Joseph Keshet at TTI. This is a theoretical talk. Just how many people have ever published a paper whose point was a generalization bound or some cult-like conference on learning? Okay. So this is a theoretical talk, but not a necessarily theoretical audience. So I often give this talk to people who don't do natural language processing. I know there are a lot of NLP people here, but my favorite example that I try to use as a running example in this talk is actually machine translation. So in machine learning, we're often interested in binary classification. Does a patient have cancer or not? Right? So there's often typically COLT, the Conference on Learning Theory, studies the problem theoretically of binary classification. But what I'm going to be interested in here is the study of what we call structured labeling. And my favorite example of structured labeling is machine translation. We have some input, which is a structured object like a sentence, and we're interested in not necessarily labeling it, but decoding it into a sentence in some other language. So we can think of a decoding problem as a problem where we're given some input X, and we want to produce some output Y, where the output Y, where in the input X is a structured object like a sentence, and the output Y is a structured object like a sentence. And the way we're going to do the decoding is by optimizing a linear score. So we're going to say find the output, the decode, which maximizes a linear score, which is an inner product of a weight vector and a feature vector. And if you're familiar with machine learning theory and support vector machines and kernels, you realize that almost any kind of scoring function can be represented this way by making the feature vector sufficiently elaborate. You can make it have all kinds of nonlinear features. So even though this is a linear score, the feature map can be nonlinear. So you can represent arbitrarily complicated things this way. Okay, so this is our decoder. It's maximizing, it's producing an output maximizing this linear score. We would like, so what I'm going to be talking about is training the weight vector. We're going to hold this feature map fixed, and we're going to look at the training problem. The training problem is the problem of setting the weight vector. We would like to set the weight vector such that it minimizes the expectation over input-output pairs. So I'm going to assume here we've got a corpus of translation pairs. And we've got input-output pairs, and we've got something like the blue score that we're interested in minimizing, we're interested in minimizing a loss. I'm going to use a loss that we're minimizing. And what we would like to do is minimize the expectation over drawing a new reference pair, a new translation pair, of the loss between the reference translation and the translation produced by this decoder. Yep.
Why is it reasonable to assume that you have distribution over the y's? So I understand why. So over the inputs you have distribution. Why is it reasonable to assume that you have distribution over the outputs?
It's just a standard cold assumption that you have a distribution over XY pairs. Intuitively, there are large corpora of translation pairs, and they were produced somehow.
Unlike the quotes, in classification, where you have targets, here the y's are translations.
Right.
Right. So it's.
Well, the way I think about it is sort of a cynical way to think about it. Is we want to win the competition, right? And we know that the competition is going to have translation pairs that we're going to get scored on, and our training data is probably it's probably reasonable to assume that the training pairs are drawn from the same distribution that our evaluation pairs are going to be drawn from, and we want to win.
What next would be to say that instead of the y's, you have the true translations of x's? Because that's what you normally have in the corpora, right? You don't have the random possible translations. So you have true translations only. So
but all I'm going to need here is that there's some distribution over xy pairs. I don't need that there's a true y. Other
there can
than
be many translations.
Sure, but I think my suggestion is that the y here is not sampled from across the entire distribution of y's. It's a very biased. The y part is the one that's really biased here. X is going to be a random sample of your language utterances, but y is going to be specific to reasonable translations or close mistranslations.
But this is a joint distribution of x's and y's, and that's what it's using. Fine.
So this is a pair sampled from some corpus of translation pairs. So I build a big corpus of translation pairs. I randomly select some as train and some as test.
So the y's assume to be only. This is only over good translations, not
whatever your translation pair data is like, right? So this is a gold standard translation, a reference translation. Okay, so what we're interested in, what we would like to do is find the W that produces the best performance on the evaluation at the evaluation. Now, the problem is that the typical way of approximating this, there's a problem with overfitting, right? If my corpus is not large enough, I can make my training performance very good, but my test performance is going to be bad because I overfit. And the way overfitting is typically controlled is by adding a regularization term. So the training algorithm minimizes a loss, a sum over the training data of a loss on the training data plus a regularization to try to drive the norm of the weight vector to be down. And what we're going to be doing is giving theorems that justify this kind of structure. That give us generalization properties. Okay, now there's a fundamental problem. I've written this as L sub S. This is the S stands for surrogate. If I literally use the training loss, this decoding is insensitive to scaling W. So I could scale W, I could take W and scale it down, just multiply it by an epsilon, and it doesn't change the decoding at all. But it completely eliminates this regularization term. So regularization of the task, I'm going to call this the task loss, like the blue score, the thing we're going to get evaluated at test time. If I simply use the task loss as the empirical measure, I become insensitive to scaling W, and the regularization is meaningless. So we need a surrogate loss. We need the surrogate loss to be scale sensitive, right? So as we scale W up, this loss changes. It's sensitive to the norm of W. Okay, so an SVM, and so this is the loss, the surrogate loss function underlying a structural SVM. Yeah.
So with regards to the regularization term, it's also scale insensitive. Attack it that way.
Well, you could make the regular. I mean, an SVM is going to use. I mean, you could say W has unit norm and then work with a margin. but then the margin becomes scale sensitive. So the standard approaches work with this. The standard approach to this, an SVM approach, works with a scale sensitive regularization. People also don't always use L2. They use some other norm, but that norm also has a scaling issue. Okay, so here is, how many people have seen structural SVMs? This is the generalization. Okay, wow. Okay. This is the structural hinge loss. This is the binary hinge loss. And it's easy to, this is a standard mapping from the structured case to the binary case. In the structured case, the feature map takes two inputs. In the binary case, the label is either -1 or 1, and this is the standard mapping from between the two. Right? I can define the feature map on x, y to be this way, and I get, and I can define the margin to be this. And then the standard hinge loss looks like this. So under this standard mapping between the structured case and the binary case, this agrees with the hinge loss. Okay, I'm not going to say, I'll come back to the structure of this, I think. But this is a difference. This hinge loss is the difference between something called a loss-adjusted inference. This is maximizing the score plus the loss relative to the reference translation. So this is a loss of a weight vector on an input x and a reference translation y. And this is saying, consider the decoding, which decodes in favor of bad blue scores. It's a loss-adjusted inference. And you're saying, take a bad label favoring bad translations and take the difference between that score adjusted by the loss and this, and that's the structural hinge loss. Okay, so I'm just going to go through surrogate loss functions. This is log loss. This is, we define the probability of a decode given x. If we have our log linear model, we can define this probability in a log linear way. We take it to be proportional to the exponential of the score and then normalize with a partition function. But then if we take that in the binary case, we get this smooth curve that looks a lot like, is qualitatively similar to the hinge loss. So in the binary case, the log loss and the hinge loss are similar. One's a smooth version of the other. One thing I want to point out, though, is that in the structured case, this max is over an exponentially large set, right? It's all possible decodes. In the binary case, that's over only a two-element set. So it's not too, so it's the fact that these are similar in the binary case can be very misleading. In the structured case, I believe these are quite different loss functions. Okay. What I'm going to be talking about in this talk is consistency. So I'm going to give you a learning algorithm. What I'm going to do is define two more surrogate loss functions. We're going to talk about ramp loss and Probit loss, that both are also meaningful in both the structured and the binary case. And I'm going to be showing that those loss functions are consistent in a predictive sense. That means that in the limit of infinite training data, the weight vector will converge to the weight vector that's optimal with respect to your loss function. Right, so there's no notion of estimation or truth here. There's just optimal performance relative to the blue score. These functions are convex. So there's a fundamental convexity-consistency tension. Any convex loss function, if you've got an outlier, especially in machine translation, you're going to have reference translations which your decoder are not going to get. Right? So you've got these hopeless reference translations. And they're going to have bad blue scores, and there's nothing you can do about it. Right? Your system's not going to get it. So you're going to have outliers. You're going to have margins that are bad. So when you have outliers, they have large, the loss is large, especially for a convex loss function. The convex loss function has to assign them large loss. And that, because it's convex, it also has to be sensitive to how bad these terrible translations are. So your ultimate training algorithm becomes sensitive to the outliers. And that's going to block consistency. So a convex loss function is not going to be consistent. If you're familiar with SVMs, if you have a universal kernel, something else happens. People claim that binary SVMs are consistent, and it's because they're talking about a universal kernel. But we can talk about that if there are questions. Okay, here's the ramp loss. So if you remember the structured hinge loss, it was a difference between a loss-adjusted inference and the score of the reference translation. Here's the hinge loss. This is a loss-adjusted decode. The score of a loss-adjusted decode, it's the score plus the loss, minus the score of the reference translation. Okay, now what we're going to do is replace the score of the reference translation by the unadjusted decode, the score of the unadjusted decode. So this is the score of the adjusted decode minus the score of the unadjusted decode. And if we go to the binary case via the standard translation, we get a ramp that is not convex, right? The outliers eventually have constant loss because if these two things, once these two things agree, have the same decode, you're just left with this loss. So you get this plateau. And you can see that it's different from the hinge loss. So it's not convex. It has this other aspect to it. Here's the Probit loss, one more loss function. The Probit loss, what it does is it takes the weight vector W and adds a Gaussian noise. So if we're in d dimensions, we're going to take a d-dimensional unit variance Gaussian noise, add it to our weight vector, decode with that, take the loss, and then we're taking the expectation over the noise of the decode loss, right? So that's the Probit loss. If we take that to the binary case, we get a smoothed ramp, right? It becomes a continuous, this is going to be a nice continuous function of W, right? So we get this. But again, the fact that this looks like this qualitatively is misleading because the binary case is misleading relative to the structured case. Okay, so here are some basic properties that hold in both in the binary case and in the structured case. So the structured case is different from the binary case, but these qualitative properties hold. The ramp and the probit are both bounded to 0, 1. So even in the structured case, I should back up. I'm assuming that the task loss itself is bounded to 0, 1. Right, so assuming the task loss is bounded to 0, 1, these loss functions are bounded to 0, 1. So that's going to mean they're not going to have high loss outliers. It's a robustness property. No individual data point can have an enormous effect. Another property is that the ramp loss is a tighter upper bound on task loss than is hinge loss. And all of these properties are kind of immediate properties. For example, you get that this is an upper bound on the task loss by sticking the decode. So if I stick the decode value into here, this thing goes down, right? Because I'm taking a value that's not optimal. Right? If I stick the decoder that optimizes this into here, these cancel, right? Because it's the same score and I'm just left with the loss. And all of the properties that I just showed you are derived, it's just by finding one of these maxes and sticking in a value and realizing that this goes up or down. And okay, so we have these properties. This property was used as the original. So there was a 2008 paper introducing this structured ramp loss, and their motivation was simply this property, that it's a tighter upper bound on the task loss. Yeah?
You can go back to the chart which you showed with the Probit loss. So so the ramp loss is upper bound, but the Probit loss is not an upper bound on your...
The Probit loss is not, right. But I'm going to argue ultimately that the Probit loss is the best thing. Yeah.
Just checking. So for the binary case, the task loss is 0, 1, 0, 1 loss.
Right.
Okay, so in the next slide, no, previous, sorry. If that was going like a rectangle instead of a whatever shape it is, that would be the task loss on the picture. That's why it's a better approximation. Is that fair?
So if you look at Hinge here. So task loss is going to go, is a step function right there.
What I'm saying is the thing we're just looking at is closer to the step function than the hinge.
Right. Right. So it's, in this regime, it's closer to the step function than it would be if it went up here. Right. Okay. This is just a slide on the history of some of these ideas. So there's a question of where these are, is there a reference for each of these structured versions of the standard loss functions? So this is the structured hinge loss. Oh no, I'm sorry. This is talking about subgradient descent on unregularized ramp loss. If you do subgradient descent on this, right? So does it mean to do subgradient descent on this? Subgradient descent means you find this maximizer, and then you take the gradient of that function of w with respect to w. So you're finding a bad label and a better label, and the gradient with respect to w is the difference in their feature vectors. So there's been work in natural language which says, take an n-best list. So I'm going to argue that the following hack is approximately subgradient descent on the ramp loss. Take an n-best list of your decodes, measure the blue score on all of them relative to the reference translation, distinguish the good ones from the bad ones, take the feature vector of the good one, and the difference between that and the feature vector of the bad one, and that's a direction that's moving you toward the good one, and update your weight vector in that direction, toward the good one and away from the bad one. And the argument is that this, if you do subgradient descent on ramp loss, it's a version of that. You're taking a bad one and a good one, and you end up moving toward the good one and away from the bad one. You're actually better in practice finding the decode and a better decode, doing loss adjustment in the other direction. But this is a theoretical talk. And the theorem is easier. The theorem actually, I don't know how to prove the other theorem. The theorem works this way. Okay, so several groups in machine translation have done things like this that are like subgradient descent on the ramp loss, and we called that direct loss. And we had an earlier theorem relating the subgradient, ignoring the regularization, to the gradient of the task loss. Yeah.
So people have happily abandoned convexity.
Happily abandoned convexity. My understanding is that the machine translation community is.
Our task loss function isn't convex. It's not happy. We would love convexity, but we can't find a way to bring it nearby.
But 0-1 loss is not convex, and the theoreticians still love convexity, right? Okay, and we've recently, so this is the slide about empirical results. We've recently experimented with Probit loss directly, and shown that Probit loss shows improvements over hinge loss. There are two ways we've gotten improvement. We've gotten improvement with the direct loss update, subgradient descent on ramp loss, using early stopping instead of regularization in practice. And we've got improvement using the Probit loss with a normal regularization. These are improvements over the structured hinge loss. Okay, so now I'm going to start proving theorems. So I'm going to introduce some notation. So if I have a weight vector W, the loss of W is just defined to be the expectation over drawing fresh data, the expectation of my test time loss. Right? So this is the expected test time loss of W. L star is the best expected test time loss that I can achieve, the inf over W of the test time loss of W. What's the best loss I can achieve with any W? Okay, now I'm going to build empirical. This is an empirical loss measure. So I'm going to prove consistency. The way I'm going to prove consistency is I'm going to assume there's an infinite sequence of training data. And I'm going to look at what happens when I train on the first n. And then I'm going to let n go to infinity. So we're always training on the first n, we're letting n go to infinity. So this is the loss, the average loss on the first n training points. Okay, that's what this loss, estimated loss based on the first n training points of W. Okay, this is going to be our learning rule. So what we're going to do is this is the learning rule I had before. This is the surrogate loss function. This is the surrogate loss, the average loss on the first n training points. We're going to optimize a score, which is the measured surrogate loss, the Probit loss in this case, plus a regularization of the norm of, plus a regularizer. Okay, and what's going to happen is that lambda n is going to grow with n. So we're going to regularize somewhat harder than 1 over n as n increases. Okay, so here's our theorem. As long as lambda n increases without bound, it could increase very slowly, like log n. But lambda n log n over n converges to 0. So this is another way to think about this is lambda n could be any power of n strictly between 0 and 1. So it grows at some rate between these two bounds. It increases, but this goes to 0. Then the limit as n goes to infinity of the generalization Probit loss. So this is the generalization Probit loss equals L star. What?
With probability.
It actually with probability 1 over the sequence. Right. Over the choice of the sequence. Okay, so here's the theorem. I'm a packed Bayesian person, so that's just what I like to use. And I think these theorems are much more awkward in any other framework, because especially this theorem, because there's a tight connection between the packed Bayesian framework and this particular loss function. So there's a general packed Bayesian law. Here, what I'm going to do here is state a general packed Bayesian theorem. There are a couple of recent references that put the packed Bayesian theorem in this form. So this says that if I have a training loss, okay, so what's going on here? I've got a space of W, weight vectors. The space of weight vectors is continuous, right? So anything that talks about discrete sets of predictors isn't going to work here. So in the packed Bayesian framework, we assume a prior over the weight vectors, and we're using L2 regularization. And the natural prior corresponding to an L2 regularization is a Gaussian prior. So I'm putting a Gaussian prior, isotropic Gaussian prior on the weight vectors. So the packed Bayesian theorem, however, is completely general. It says for any set of predictors and for any prior on those predictors, what I'm going to learn is a posterior on, it's kind of Bayesian, it's going to learn a quote posterior on the predictors. And the way I'm going to use that posterior at test time is I'm going to randomly draw a predictor from the posterior and use it. Okay, so the loss of the posterior is the expected loss over drawing a predictor from the posterior on predictors. So this says that the generalization, so with high probability over the draw of the training data, simultaneously for all possible posteriors Q, for all possible weights on the space, the generalization loss of that posterior is bounded by this expression in terms of the training loss of the posterior. Now this is the training task loss, but we're drawing from the posterior, so it's going to actually become scale sensitive. Plus this thing that depends on the KL divergence between the posterior and the prior, and a confidence parameter, and the number of points of your training data. And this, so all I'd have to do here is pick my regularization parameter before I look at the data. right? This is to make this exactly hold. So it's a very nice, simple statement. And you can see that the regularization parameter can't get too large before this term doesn't matter, before this term becomes close to 1. So this is sort of predicting the regularizer in some sense. This theorem is sort of saying your regularizer should be roughly order 1 in this formulation. And in this formulation, we're getting something that looks very much like regularized minimizing exactly what our learning rule is minimizing. So so now what I'm going to do is I'm going to say, okay, what I'm going to want to do is bound a certain loss of a weight vector w that I'm learning. So my prior is centered around 0, right? My prior is a Gaussian prior centered around 0. I want to say something about some w that's highly non-zero. So I'm going to take my posterior to be centered around w with the same isotropic Gaussian distribution. So that distribution is exactly the distribution I get when I add Gaussian noise to w. Right? So adding Gaussian noise to w defines a posterior over the distribution. I simply plug that posterior into this formula, and this becomes the Probit loss of w. Right? That is the Probit loss of w. This is the empirical Probit loss of w. Right? And I get this equation, this bound. So now, basically, this is going to give you the theorem. Right? So the theorem says...
So L of Q is the expectation of the loss over draws from Q.
Right.
And the reason this works, it seems, is like because you've got an expectation in the probit that L Q is taken care of. Right? The expectation of the noise
Right.
is going to reappear in that.
Right. Right. Yeah, this is an expectation over noise, so it's drawing from Q, essentially. And the same is true here. This is the empirical performance when I draw from Q. This is also the empirical performance when I draw from Q. Okay, now we're interested in proving consistency, so we're interested in taking n to infinity, and the conditions I gave on lambda n are going to be such that this term is going to go to 0 as n goes to infinity. And the reason there's a log term that's actually coming from this. The other thing I'm going to do is let my delta term go as 1 over n squared to get probability 1 over the sequence. And then if this term is going to 0 as n goes to infinity, but I still have this inequality, and lambda n is going to infinity, which means this is going to 1, I'm getting that this term is dominating this term. And then I have to argue that I can take I can consider particular w's of increasing norm, and for w's of sufficiently large norm, this term is going to converge to L star. That's a little, the paper has a little bit of a careful argument there that basically what you want to do is say so L star is defined to be the inf over W of the performance of W. In the proof, I have to say, well, consider any reference W. All I have to prove is that my performance gets at least as good as any reference W. If I hold a reference W fixed and take n to infinity, the algorithm is going to minimize this, right? So what I'm going to get is that, do I have a better slide with this? No. So all I have to do is prove that I do as well as any reference W. I pick a W. I have to prove that I'm doing as well as that W. My learning algorithm is going to be minimizing this expression. The learning algorithm is going to pick something whose Probit loss here, as n is going to infinity. I also only have to look at the limit as n goes to infinity. The learning algorithm is going to pick something whose empirical Probit loss is doing at least as well as W. And I can also, at the same time, consider scalings of my reference W. I can scale it up to be larger and larger. And as I scale it up to be larger and larger, we can prove that this empirical Probit loss becomes a valid estimate of the true generalization loss for that particular W as its norm goes to infinity. It's a somewhat... When I've given this talk before, I've really cheated at this point in the talk and said, this is a straightforward argument now. There's one issue in this theorem that some people get upset about, in that what I've proven here Where's my consistency theorem? What I've proven here is that the Probit loss of my estimator is converging to L star. I have not proved that the loss of my estimated W is converging to L star. And I justify that by saying, well, this Probit loss can be realized. I can actually just implement the process that adds Gaussian noise, make predictions. So it's giving me a prediction algorithm whose performance is approaching L star, because I can achieve this loss. The reason I can't get that L approaches L star has to do with the fact that in infinite dimension and with latent variables, even though the performance is converging, you can construct this weird example where the vector W is rotating in an infinite dimensional space forever. And it's not actually, the direction of W is never converging. Okay, so here we're going to do the analogous thing for ramp loss. This becomes much more, the proof of this is much trickier. But now we're going to replace the surrogate loss with ramp loss. So this is the empirical ramp loss. We're going to minimize the empirical ramp loss plus a regularized term. And the theorem is very similar. There's like a logarithmic factor difference in the theorem, right? So it's still going to be true that for if the regularization is a power of n, where that power is strictly between 0 and 1, we're still going to get consistency. So this theorem looks deceptively like ramp loss is similar to Probit loss. I'll say why that's not going to work, or why it's deceptive later. But it's essentially the same theorem, up to a logarithmic factor. Okay, and how does this theorem work? We have this inequality. We know that ramp is an upper bound on task, right? And we know that the limit as the weight vector goes to infinity, or equivalently, as if we think of adding noise with variance sigma, if we take the variance to 0, that's equivalent to taking this weight vector to infinity, that we have this system of inequalities. So what we want to do is find a finite rate as a function of sigma that relates the Probit, that relates the Probit to the ramp loss. So we're going to get, so we know that the limit as sigma goes to 0 of this expression is less than the ramp loss. And what I'm going to do is I'm going to give a finite rate for that in terms of sigma. Okay, so this is our theorem that the Probit loss is bounded by the ramp loss. The Probit loss at a finite sigma is bounded by the ramp loss plus a penalty that depends on sigma. Okay, so that's what I'm going to prove. I'm taking this inequality in a limit and giving it a rate. So at the top level, what I'm doing is I've got a bound in terms of the Probit loss. I just argued for that based on this Bayesian theorem. And what I'm going to do is I'm going to give inequalities relating ramp to Probit and then use the bound on the Probit loss. Okay? And I've got this. So should I skip this slide? I can see people fading away. Yeah.
The last term which measures the complexity of the white space can get.
Oh yes, sorry.
Bad, right?
This is the number of possible decodes, right? And that's bad, but at least it's in a log. So this is, you can think of this as the length of the sentence. That's still bad. I believe that using Johnson-Lindenstrauss, we can actually prove that we can get that down to log-log. In the original paper, Kohler-Gestron and Tasker, Kohler and Gestron on the structural hinge loss, they proved a theorem with a log-log term here, basically, in their particular setting. I think you can get a log-log in general. But yes, this is the number of possible decodings, and that's a troublesome term. Let me just give you the essence of the idea. I'm not going to go through all of this. I'm just going to let's just look at this one line. What's going to happen here is I'm going to say for every possible, so we've got the space of possible decodes. I've got an input sentence and the space of possible decodes. For every possible decode, there's a margin. What do I mean by the margin? I mean take the decode that the system's actually producing. That's the best scoring decode. Every other decode is going to have a score worse than that. Take the gap between the two scores, and that's the margin of a potential competing decode. Sometimes these competing decodes are called distractors. The biological community likes to call them distractors. So every distractor, every alternate decode has a margin. The idea is that there's a certain threshold on that margin, which provably that anything whose margin exceeds that threshold can be ignored. Right? It's just not, the decode is not going to be that when I add noise to the weight vector. So the idea is that the Probit loss is less than this thing. There's going to be something handling the fact that it's not completely true that I can ignore the bad guys, the things with large margin. But I can basically look at the maximum, that the Probit loss is less than or equal to sigma. We're going to take sigma to 0, plus the max over all the plausible decodes of the loss of that plausible decode. And that's the fundamental proof method in getting something for ramp loss, right? Because this quantity, the max over plausible decodes, is something that I can relate to ramp loss. And this threshold is just picked to make this theorem true, such that when I do a union bound and a high probability deviation bound. And then this is just finishing the proof. It's taking that first thing and doing a sequence of steps that relate it to the ramp loss. This max can be replaced in here by a max over everything. And then this becomes the decode. This becomes equivalent to a loss-adjusted inference, and you get it related to the ramp loss without going through a lot of details there. And then, using this inequality, this main lemma, this says the Probit loss is less than or equal to the ramp loss plus this. I get this generalization bound for the ramp loss. This is saying the generalization Probit loss of W over sigma is less than, and all I've done here is I've taken the Probit loss and replaced it by an upper bound, by the upper bound I just proved. Right? So the Probit loss was upper bounded in terms of the ramp loss, and I've replaced the Probit loss in the original theorem by the ramp loss here. And now I've got a generalization bound I've got a bound on the generalization Probit loss in terms of the empirical ramp loss. And now we can just take schedules for sigma and lambda and get our theorem, get our consistency theorem. Okay, now the other thing we can do, rather than just taking schedules for these to get our theorem, the other thing we can do is actually sort of optimize away sigma and get a generalization bound directly in terms of the ramp loss. So it turns out that this is an approximately optimal value for sigma to minimize that bound. And now we get a finite sample generalization bound in terms of the ramp loss. So this is saying that the generalization Probit loss is bounded by this thing in terms of the ramp loss. And really, I think that these consistency theorems, these asymptotic consistency theorems, are not so interesting. What's much more interesting to me are these generalization bounds, because this is providing a concrete finite sample generalization guarantee. Right? It's telling you more than any kind of asymptotic infinite limit statement. So this is the finite sample guarantee we had for generalization with respect to using the Probit loss as the surrogate loss. When we optimize away sigma, here's the analogous guarantee in terms of ramp loss. But now look at the differences between, what I want to focus on is this regularization term and this regularization term. So this term is linear in lambda in this part of it, lambda times w squared over n. This is lambda times w squared over n to the 1/3. So what this says is that for the bounds we've been able to prove, the ramp loss bound is significantly worse than the Probit loss bound. And it could be an artifact of the proof technique because the proof technique was natural and immediate for the Probit loss. But I think my feeling is this is real, that you're better off using this Probit loss. Okay, so I'm basically done. I've skipped some of glossed over some of the technical details. And the summary is we know we need surrogate loss functions if we're going to regularize. And we have all of these standard surrogate loss functions from the binary case that generalize to the structured case. I haven't talked about it, but all the theorems in the paper also are actually written for the structured latent case. So in the structured latent case, I optimize not only over the decode, but I also optimize over latent information like parse trees or what have you. And all of this analysis generalizes to that case as well. And we have Probit and ramp that are both provably consistent, but I believe they're significantly different in the structural setting. Yeah.
So your intuition as to why the convex loss functions are not consistent is that they are unbounded. They just keep going up.
Which makes them sensitive to outliers.
So that would suggest that if you consider, for example, the class of monotonic functions that are bound, like the two that you've got, but they're still not atomic. Maybe, could this generalize to all such functions? You pick two particular functions, they have a rather similar shape. Could all such bounded monotonic functions maybe be consistent, or is it just...
Well, that's almost certainly true in the binary case. And there's lots of theory about that uses a Lipschitz bound. They have to have a Lipschitz constant associated with them, and then the bound comes out in terms of the Lipschitz constant. I would have to think about what properties you might need for the... probably there's something like that for the structured case. Yeah. So, the theoreticians talk.